All right, perfect. Yeah, thank you very much. And let's get started because there's only 20 minutes left in this talk. So I'm Adrian, I'm one of the co-founders of Anoma. And today I'm going to talk to you about Declarative Decentralization, the final rails of Web3. And really the way to think of this is that declarative decentralization implemented as an Anoma allows you to have one architecture for full stack decentralized applications. And I'll go into depth what this means today. So I want to quickly go a little bit into the background here because I think most people keep forgetting this, especially if you're in the dApp world. We had generation 1 and generation 1-like systems, and I really call this generation scriptable settlement. This is Bitcoin and Bitcoin-like systems. This even includes things like Zcash, Monero. They all had roughly the same API that was exposed to application developers. And you could build some applications on it, that's true. You could build things like colored coins, Namecoin, the global Bitcoin stock exchange. Like if you've been around long enough, you remember that in like 2014 or so, there was like an unregistered securities exchange run out of the US called the global Bitcoin stock exchange, on which you could actually trade tokenized shares. It worked, but it was clunky. Like none of these applications were composable with each other. You had to fork Bitcoin core in C++, run your own network in order to make this work. And this pretty directly led to Ethereum, or what I would call generation 2. Systems that have programmable settlement. And all of a sudden, you didn't have to worry about running your own chain to run colored coins. You moved colored coins to ERC20s, you moved things like Namecoin to ENS, and you got a whole lot of other fantastic new things that you couldn't be building before. Like you could get DAOs, you could get soul-bound tokens, things like NFTs. Generally speaking, the level of complexity in terms of what was possible with regards to applications increased by like an order of magnitude roughly. And so as a result, nowadays you can build DEXs, AMMs, NFT marketplaces, and so on. Again, this works, but it's still clunky kind of, because you need to build a lot of backend infrastructure to make a thing like a 0x protocol work or something like OpenSea work, because Ethereum just does the programmable settlement. And I will go into more detail in a bit on there is probably 80% of the rest of the application that can't currently be handled on Ethereum. Because generally speaking, all existing applications require at least one centralized component. Because the modern design pattern of dApps is really that users don't have transactions, users have signed messages. Because if you want to, for example, do a trade, I don't have a transaction that's executable on chain, I have a partial state transition that goes from A to B. I don't have a thing that also takes the other side and that's directly executable on chain. So, for example, in the case of OpenSea, the way this works is that the user has a signed message. They send this to the centralized Web2 server run by the OpenSea team in San Francisco on AWS. That centralized server collects a bunch of these messages. Different people call this sequencing or solving, it doesn't really matter, or matchmaking. The pattern also applies to things like Optimism, for example. It's again the same pattern. Users don't have transactions, they have signed messages. They send them to some centralized Web2 server that does some compute over a set of messages, and then the computer settles the net state changes as a transaction on Ethereum. And I know historically everyone keeps talking on that all these systems like Near, Avalanche, Tezos, Solana, whatever, that they're like Polkadot, Cosmos, that they're really generation 3 or the next generation of blockchains. I think I hold the very controversial opinion that this is not the case. They're like incremental improvements over Ethereum, because structurally speaking, the kind of applications that you can build on something like Avalanche, Near, or Solana are exactly the same things that you can build on Ethereum nowadays, with a slightly different consensus, with a slightly different speed. But fundamentally, from a developer perspective, the APIs that you have access to, the guarantees that your application gets, are exactly the same. I mean, we've had a number of advances, right? We had like advances of Sybil resistance, moving proof of work to proof of stake. We had scaling solutions like sharding, rollups, or just fast single state machines. So there were many improvements over time, but they were incremental improvements that didn't fundamentally change what was possible from an architectural perspective. So I would consider all these systems generation 2x, kind of like programmable settlement plus plus. one of the big insights, though, that for most modern applications, settlement is not sufficient. And so I'll start here with some historic context again on like why we ended up in the settlement-based world. It's because everyone, like this all comes back from Bitcoin. It comes from the idea that Bitcoin was supposed to be used to buy milk in a store. And if that's the use case, then you have a transaction as a fundamental unit, because you have the counterparties that are physically in front of you. You have the thing that you want physically in front of you. But most applications within the blockchain space didn't play out this way. That like, we try to do global settlement systems that allowed you to trade Bitcoin for ETH with someone halfway across the globe. And here settlement is not sufficient, because settlement fundamentally means that parties already know who they are and what they want. Most actual applications need counterparty discovery because they need help to find sort of the other side of the trade. Good examples here are DEXs with marketplaces having buyers and sellers, even quadratic public goods funding, project donors and funders falls into this, DAOs falls into this category, any rollup falls into this category, because fundamentally in these systems users don't have finalized state transitions that can be settled and executed on chain. They have partial things that need to be combined with other people's partial intents in order to form a fully fledged state transitions. I just quickly want to go into like what are the current approaches to counterparty discovery. There are roughly 3 approaches to this. One, you do it on the blockchain. This is what Uniswap and AMMs do. It's kind of silly and incredibly expensive, but it is the most decentralized way to do counterparty discovery in current systems. I would consider that I think a lot of people believe that AMMs are sort of a global optimal design. They're not. They're local optimum created for sort of the constraints within within Ethereum. They are not perfect in any sense because they are the most expensive way to do decentralized counterparty discovery within the current systems. You can also do the other thing, which is you run a single operator database. Things become very easy if you just have one server doing all the coordination. This is pretty much what every decentralized, and I'm using air quotes here deliberately, decentralized application does. When you look at something like OpenSea, Optimism, Starknet, Arbitrum, they're all single operator databases. There's like one Web2 server, and if that Web2 server wants to censor you, they can. In some cases, the Web2 server can also steal all your funds because fraud proofs aren't implemented yet. But so these are that's the second approach, and this is what most people currently use between like OpenSea, 0x, Flashbots, roll-up sequencers, ZK provers. These are all trusted third parties that you as a user have to consider in your trust model. The third approach is you can also do an app-specific sovereign chain, which is effectively you go back to step 1, but you do it on a custom blockchain. So you pretend like the fundamental scaling limits don't exist because you can dedicate all your throughput to this one thing. Fundamentally, it's exactly the same thing though, because structurally you made no improvements, you made no changes. And one of the big problems here is that above all, you lose composability between applications. So when you consider what happened when we moved from Bitcoin to Ethereum, all of a sudden applications started becoming composable at the settlement layer. So my contract could call into someone else's contract, and I could build applications this way. And so we got about an order of magnitude more composability this way. Here, a signed message sent to OpenSea, to Arbitrum, or to Optimism, I as a developer can't build a new application that leverages existing signed messages or existing intents. So we're losing the composability here because really, from a user perspective, it doesn't matter which optimistic roll-up I'm in. I just care that I'm in some that has roughly equivalent security guarantees. To an actual user, it doesn't matter whether they're an Optimism or Arbitrum. They just want a fast, cheap, optimistic roll-up. This is currently not possible because none of these applications are composable at the intent level. Yeah, and so now I'd like to take the last couple of minutes to go over the evolution of protocols towards generation 3 architectures that allow you to build full stack decentralized applications. And I mean, so we've called the architecture Anoma a unified architecture for full stack decentralized applications. I have to say this is not to say that Anoma is the only thing that can possibly exist. It's more, I would expect that all future blockchains sort of being built from now on will follow a roughly similar design pattern, because it is the design pattern that solves the structural issues that exist within Generation 2 architectures. And it's one architecture that provides intent centricity, composable privacy, decentralized counterparty discovery, distributed solving, as well as multi-chain atomic settlement. And the talk is actually titled Declarative Decentralization, the Final Rails of Web3. And here I'll sort of go into what this actually means and why declarative paradigms are the things that are going to exist in the future. And I'll start with a quick overview of how this currently works. Currently, our systems are fairly imperative. When you think of what an Ethereum transaction is, it's an execution trace. It is a user signs over a function call and an entry point there, and then sort of arbitrary compute happens. A user doesn't sign over a specific state change. So they sign over the how to achieve their state change, not exactly what state change they want to achieve. And intents are completely different here. Intents are fundamentally that users sign over what they want to achieve, but don't specify how to do it. And I would argue that this is going to be absolutely necessary for mass adoption of decentralized applications, because it is fundamentally safer and more scalable. Like, my parents can understand the model that, like, if they sign over a message that says, I'm trading 1 Bitcoin against 100 ETH, that's the state change they're authorizing. My parents will never understand how to audit every single opcode that could be possibly involved in their call stack when they sign an Ethereum transaction. And I mean, there are some other advantages here. Once you switch your mind to this idea of declarative decentralization, you get a lot of advantages. Like, you get decentralized counterparty discovery almost for free, because it's very easy to, I have an intent that says I want to trade like 1 Bitcoin against 100 ETH. And to me, at that point, it doesn't matter whether there's one counterparty, whether there's a pool, whether there's 1,000 counterparties across the globe, because I just specify which state change I cared about, not how to get it. Again, this is kind of where we hit this local optimum with AMMs in Ethereum, that, like, instead of figuring out how to do decentralized counterparty discovery and declarative decentralization, we figured we can just make one large counterparty, as in the pool is the counterparty and everyone just interacts with the pool, right? The other cool thing is intents are composable, so that if I trade A for B and you trade B for C, someone else 2 days later can trade C for A, and we can take these 3 intents that are not individually settleable without having to go via a centralized counterparty and just settle them directly, because as a group, they all get fulfilled. Yes. So this is really how this architecture as a result looks, with a declarative black box architecture that users really just create intents that specify what specific state changes they care about. This could be, I want to be in a rollup, I want to be in a multisig. This pretty much generalizes to all existing systems, because fundamentally the base unit that people actually have is intents, not transactions. They submit them to some settlement system or to some execution system. This could be Anoma, this could be others. And then the system sort of figures out what is the best path to execute and fulfill and settle the state change or this intent. And in the end, a user just has to check the updated state. So what's actually in the black box? Because sort of this was the conceptual introduction to why declarative decentralization is going to matter. But what do you actually put into the black box to enable this? And here, really on the far left, we have counterparty discovery. So here, users can issue transparent intents that are either transparent, shielded if you use zero-knowledge proofs, or private if you use fully homomorphic encryption. They submit those intents to the intent gossip layer, which is a globally non-consistent sort of P2P network, as in different intent nodes can have different views of the network, because none of these intents are yet consensus critical. These get gossiped around. Solvers look at this and go, okay, which ones of these are compatible with each other? Which ones are combinable? For example, 2 NFT trades that match each other are 2 compatible intents. And the solver would find these and say, okay, let me put them into a transaction and actually settle them on chain. This could also be that there's a rollup sequencer that says, well, these 15 things now pay me enough fees to justify running the rollup computer or running the ZK prover for my ZK rollup. And then takes the sequencer or the solver takes those 15 intents, computes the ZK prover, the ZK proof, submits the updated state root to Ethereum. Or to Ethereum or to Anoma, actually, to like some settlement system. Then you have the consensus part, and here really, once the solver has found a solution, they submit this as an encrypted transaction that is not front-runnable, because once you start redesigning protocols from first principles, front-running is actually not a difficult problem to solve. You can just use something like Fairview to provide programmable threshold decryption and encryption, that all transactions are initially encrypted against the shared public key of the network. Then encrypted byte strings are stored into blocks. And on the next block, once the ordering has been fully finalized, those transactions are decrypted and then executed. At that point, no one has an unfair information advantage that they can use to front-run, back-run, or sandwich you. Yeah, and in the end, if you want very good privacy guarantees and incredibly cost-efficient settlement, you want something like Tiger, which is our unified execution environment that handles transparent, shielded, as well as private state. By the way, all of this is like open source code, and you can just look this up later on github.com/Anoma. One of the cool things here is that Anoma is an architecture. It's not a specific deployment model. You can take Anoma as an architecture and deploy this as an L1, as a globally decentralized L1 run by a global community. You can decide to take Anoma as an architecture and deploy this as a proof of authority chain to run commerce in New York. You can decide to deploy this as an L2 to Ethereum or to some other existing settlement layer. But the nice thing is you still get total composability over all the intents, because you have one global intent pool that connects all these different deployments of one architecture. For the benefit of time, I'm going to quickly skip over these. You get a bunch of novel primitives. You get like Tiger for composable privacy, you get Fairview for programmable threshold decryption, which actually enables you to do programmable batching on chain. So think something like CowSwap, but fully decentralized, where users encrypt their individual intents against the shared public key of the system. Those intents are stored on chain, and only after the application-defined batch is over do the validators jointly decrypt all the intents within one batch, and then solvers, in the same sense that solvers exist in CowSwap nowadays, can take those intents, compute an optimal solution, submit this, and then on the application side, the application can enforce a sort of optimality criteria, as in everyone gets the same clearing price in a single batch. Yeah, this is actually the example for this, but the other thing, when Ethereum came out in 2015, we really couldn't spell out all the applications that it would enable, because everyone was like, well, this seems just like Bitcoin, but slightly more programmable. Most people didn't yet realize how much more composable Ethereum was going to be. And it's kind of the same thing here with Anoma as an architecture. Anoma is probably going to make things about an order of magnitude more composable than existing things on Ethereum. Not on Ethereum, actually, like existing architectures. This isn't to like shit on existing architectures. It's just like there are going to be new architectural advances. Yeah, you can build contemporary applications here. You can also build a bunch of novel applications, and I'm not going to go through these in depth. I think sort of the most intuitive one is you can build private OpenSea, where individual users are completely private, even to the solvers that solve the trades. So you can privately trade your NFT for some ETH. This is currently impossible to be built on existing architectures, simply because of how the privacy guarantees are structured in existing architectures. Maybe just like one last comment here is, fundamentally the direction we need to be moving in as a space is towards homogeneous architectures but heterogeneous security models, because not everyone cares about the same security model. Like my parents don't want Ethereum security. My parents want like local village proof of authority chains run by the local authority. And we should just always consider, how do we make unified architectures available to people no matter what security guarantees they actually care about. This leads also to fractal scaling, to Typhon as a new consensus architecture, and yes, thank you very much. This is Anoma, one architecture for full stack decentralization. I don't have time for questions, so find me next to the stage.